So to recap, last week what we talked about was a lot of information about PV isotherms, right? Pressure versus volume as a function of an equation of state. Now specifically, we plot pressure versus volume for a cubic equation of state. It'll look something like so. And again, this region where you get some interesting characteristics and changes in shapes is going to be difficult to find. We call this an isotherm because the temperature is equal to a constant, or following along a path, dt, or the rate of change of temperature, is equal to 0. Same thing, right? If you take the derivative of a constant, you get 0. The reason for this particular region being very difficult to identify is a couple of reasons. Number one, we don't oftentimes think in terms of specific volume. So if I were to ask you what's the specific molar volume of liquid water, you guys might be off by 2 or 3 orders of magnitude. Right? It's probably like 0.003 or 00, something like that. It's a very small number. The other problem is that when we draw out our dashed line here, this will be our vapor pressure at that particular temperature. Right, this is one of our goals that we're trying to figure out when we do a phase transition using a cubic equation of state, is that the density of the liquid and the density of the vapor, they're going to be off by a couple orders of magnitude as well. So if you're looking at this plot on a linear scale, you're going to be sitting somewhere over here where at 10 to the minus 3, you're going to have something that's much higher up over there. Again, like I said, I think it's about like 10 to the minus 3 or so. So if you're plotting it out, you'll be like 1, 2, 3, 4, 5, and you're going to miss this kind of region over there. Now don't quote me that it's exactly 10 to the minus 3. So what we ended up doing is if we integrate from this point to this point over here, following along a path of constant temperature, but integrating VdP. Double check that I have that right. Go back to my, oh no, I have that right. So if we go across the path of constant temperature, this is 0. When we integrate dg, it gives us delta g, which we know is 0. So we integrate along a path of VdP, which is a little bit weird, right, because we integrated to the y-axis. But the conclusion was that this negative area and that positive area canceled out. I didn't draw it very well. So if we wanted to use a cubic equation of state, we could integrate the equation of state, substituting in an expression for volume, which oftentimes we don't have. Right? Most of the time, these cubic equations of state are pressure explicit. Right? The van der Waals equation. Right? This is a pressure explicit equation, so it is not possible to rearrange this in terms like what we see here. So we'll have to transform this out instead of going from dp to dv. And further, the limits of your integration here and here, those aren't even easy to find as well. So if you guess a pressure, we may or may not know that it's the right pressure for the vapor pressure. Right? We guess a pressure. These roots already involve the solution to a cubic equation of state. So we have to solve this expression here. There's going to be 3 roots, 1, 2, 3. The middle root is not going to be a thermodynamically stable fluid, so we neglect it. The smaller of the 2 roots corresponds to the liquid. The higher of the 2 corresponds to the vapor specific volume. Then once you've completed that step, then you have to go ahead and actually integrate this expression. So if we wanted to apply this numerically, we would more or less have to discretely plot out this function with a particular resolution, solve for the roots of the van der Waals equation of state for every one of our pressure guesses, and we'd have to repeat those pressure guesses until we find the right pressure that satisfies this relationship here. So it's a relatively cumbersome process. Yes, we can extract phase data from a cubic equation of state, but it does involve a significant amount of work. One step that we are going to take is, instead of trying to solve phase equilibrium graphically or visually, we're going to invent a new concept. And this new concept, called fugacity, is a useful convenience for solving a problem like this, but it becomes an absolute critical necessity when we discuss multi-component mixtures. So for now, we're going to be defining fugacity for a single component system. And then we'll have to expand upon all of this and redo a lot of everything that we're doing once we transition to multi-component systems. Okay. So our equilibrium criteria is that the Gibbs free energy is our equilibrium criteria. For a liquid to vapor phase transition, but this holds true regardless. We could say this is phase 1 and this is phase 2. That our Gibbs free energies have to be equivalent. Likewise, we can write out our Gibbs free energy for changes in temperature and pressure. This is the combined first and second law. The only thing that we've done to get to this equation right here is define the Gibbs free energy, define the temperature, define the pressure, and then more or less substituted everything together with a whole bunch of calculus and tedious math. So if we're looking at a process where we're varying the pressure but holding the temperature constant. Now this is very similar to what we did when we talked about state changes with an equation of state, where when we had a similar plot, but in this case here, we looked at PT plots, pressure versus temperature, and we wanted to go from state 1 to state 2. The path that we decided to take was to depressurize to 0 so we can get to an ideal gas state, heat it up as an ideal gas, meaning we only have to tabulate the heat capacity properties of an ideal gas, and then repressurize. So only these steps here and here required us to involve any sort of non-ideal or real fluid properties. And from that, we were able to use an equation of state to figure out how we should integrate, changes in enthalpy or changes in entropy. So similar approach here, right? This is the real challenge. The ideal gas problem is relatively straightforward. We basically have all the relationships that we need. So the only thing that we need to solve an ideal gas problem is ideal gas heat capacity. So for phase equilibria, we want to take a similar approach, where we're going to set our temperature and then change the pressure and then try and figure out the properties that go on from there. So if you look at the Gibbs free energy change, that's for ideal gas. It's just VDP at this stage. Now this is valid for any true real fluid. In fact, it's actually true for solids or whatever the case is as well. No assumptions have been done right now. All we are doing is we're following along a path of varying the pressure but holding the temperature constant. Now for an ideal gas, we can have the same approach. Gibbs at temperature 1, pressure 2. That's the final state, right? This is delta, so this is final minus initial. I'll try and write less crooked. Yeah. All that was done is substitute in the ideal gas law for here. So what we're going to do is we're going to set the initial pressure to equal to 0, meaning that we're going to start off at an ideal gas state. I'm going to call this expression equation A, this expression equation B. B. Now what this is effectively doing is calculating what we call a departure function, meaning it's the deviation between the real fluid properties and the ideal gas fluid properties. This is another trick that's done in thermodynamics to avoid unpleasant discontinuities. Recall, for example, that if we take a system at a finite pressure and we depressurize it to 0, that new system effectively has an infinite entropy. But we know that at some point we're going to go back from an infinite entropy to some finite value. The departure function doesn't have that complication. So the departure function is a way, doesn't actually change the math, it just makes it a little bit more convenient. So you'll find out in this week's homework, when we're calculating state changes of real fluids, you either have to carry out the math symbolically or deal with the fact that you have an infinite entropy, for example. So from here, we can effectively, I'll do one more step, then we'll define the fugacity. Gibbs energy, so the Gibbs free energy at some temperature and pressure minus the Gibbs free energy of an ideal gas at the same temperature and pressure. And that's the goal of what we're doing here by taking these two steps. Right, because in this equation here, expression A and B, this term, this is the ideal gas state because it's at pressure 1, which is 0. This one's at pressure 1, which is pressure 0. So these terms cancel each other out. So we're just left with these two lingering ones, the ideal gas and the real fluid. Okay, this is the Gibbs departure function. How does the Gibbs free energy of a real fluid deviate from the Gibbs free energy of an ideal gas fluid at the same temperature and pressure conditions? And effectively, it's how much it differs from the real fluid specific volume versus the ideal gas specific volume. And from here, this is all we need to define the concept known as fugacity. The fugacity is no more than a scaled version of the Gibbs departure function. Okay, so the definition of fugacity, we write it with a fancy curly F. A few more definitions. We can define the fugacity coefficient as simply the fugacity divided by the system pressure. Box it to make sure it's really nice and clear that this is an important definition to have. If the pressure is low, the fugacity is approximately equal to the system pressure, or the fugacity coefficient is close to 1. The question here is why fugacity? Why bother? Well, the main reason is that a lot of the unpleasant property changes that we experience also follow the behavior that an ideal gas does. So these issues here of infinite entropy when you go to zero pressure, that's captured all within the ideal gas state. Another good reason is that a lot of the calculations that we do, ideal gas calculations, are assumed to be something that everyone who knows thermodynamics should be able to handle. And for the most part, ideal gas calculations are relatively straightforward. It's really just changes in heat capacity. If it changes as a function of temperature, we just have to integrate it, but they always correlate it using those polynomial expressions, so it's really easy to handle. And then on your equation sheet, if anyone has it out in front of them, you see there's like 3 different relationships for entropy changes with respect to ideal gases. And that's really about it. So the notion here is that we don't really want to necessarily keep track of every single ideal gas calculation, so the easier approach is just to lump it together and say all we care about is the deviation from ideal gas behavior. But the true purpose of the fugacity comes with multi-component systems. For single component, it's convenient to introduce the concept of, but it's not critical. We can solve phase equilibrium without the fugacity for a single component system. It's much more difficult to solve phase equilibrium for a multi-component system without the definition of fugacity. Okay, so let's look at the equilibrium criteria. So using fugacity, we can demonstrate that it's just the same thing as if we use the Gibbs free energy. So we don't actually have to use that the Gibbs are equal across the phase transition. We can use that the fugacities are. So at equilibrium, the Gibbs free energy of phase 1 at some temperature and pressure is equal to the Gibbs free energy of phase 2 at some temperature and pressure. And that's how we know that we're in chemical equilibrium. We also know that at chemical equilibrium, temperature and pressure across the phase has to be the same as well. That's our thermal and mechanical equilibrium criteria. So if we rearrange the definition of fugacity here, we can write that the Gibbs free energy can be extracted from the fugacity. Gibbs is a function of temperature and pressure. Ideal gas Gibbs is a function of temperature and pressure. Fugacity is a function of temperature and pressure. All of these are functions of temperature and pressure. So if we substitute our fugacity expression into our equilibrium one, and this is for phase 1, fugacity of phase 1 gives ideal gas of phase 2, temperature and pressure. Fugacity of phase 2. And if you really wanted to be meticulous, we could add in a temperature phase 1, pressure phase 1, temperature phase 1, pressure phase 1, temperature phase 2, pressure phase 2, but we already know that those are the same. So temperature phase 1 is equal to temperature of phase 2, pressure of phase 1 is equal to pressure of phase 2. The Gibbs free energy of phase 1 ideal gas is equal to Gibbs free energy of phase 2 ideal gases. Ideal gas law doesn't predict phase transitions, so an ideal gas is an ideal gas. Right, so that cancels with this. The RT cancels with the RT. We take the exponent of both sides, the exponent of both sides, the pressure cancel. And we find that the equilibrium criteria in terms of fugacity is exactly the same as the equilibrium criteria in terms of the Gibbs free energy. So we can use fugacity to do all of our phase equilibrium calculations, and we don't have to worry about calculating the Gibbs free energy. Okay, let's talk about how we calculate the fugacity and see how we can actually apply it to solving the problems that we're worried about. Phase transitions for a single component is what we're focused on right now. So we'll start off with the fugacity of a vapor. Quick question, who knows the difference between a gas and a vapor? What's the technical, tedious thermodynamic definition? Anyone want to venture a guess?
Well, when I hear vapor, I think of water, like water vapor.
For the most part, the water that we deal with is in a vapor form. Yes?
It's about the critical temperature?
It is. Which of these two is critical and which one's subcritical?
Gas is above the critical
Yep.
temperature?
Gas is above the critical point, vapor is below the critical point. So when it comes to fugacity, typically we only really care about the fugacity of the vapor. We don't really care about the fugacity of a gas. The reason for that is fugacity is most useful for phase transitions, and gases can't undergo phase transitions. If you're above the critical point, you're supercritical, and there is no phase transitions that are available. Right? There's no transition between a gas and a liquid or a vapor and a liquid if you're supercritical. But for a vapor, there is a phase transition. When you pressurize a fluid isothermally, eventually you'll condense it. If you pressurize a gas isothermally, you'll never condense. So if we draw out a couple of different isotherms, so if you're subcritical, you'll get one of these little features like this on the isotherm. At the critical point, you hit an inflection point and it goes back down. Supercritical, you never have an inflection point. So if I were to take a gas right here, that's supercritical, and I reduce sorry, it's PV, my bad. And I compress it isothermally, it will never hit that phase transition. Likewise, a vapor, though, will eventually hit a phase transition and turn into a liquid. And remember, this curvy up and down path is not the path that the fluid actually takes. Once it hits the saturation point, now we don't know what it is, but we know how to calculate it now, it then instantaneously jumps down to the liquid phase. And that's that discontinuity that we see when we see a phase transition. Okay, so fugacity of a predominantly vapor, but you may need to use this relationship, I guess, in other forms. Effectively, it's exactly what we just defined already. Right, so I'm just going to rewrite it, but for the sake of It's a little bit different, more compact here, having the natural log over on the left-hand side. This is the specific volume of the real fluid. This is its deviation from the ideal gas behavior. We integrate it with respect to pressure, going from an ideal gas state, which is pressure equals 0, to some finite state. Then we scale it based on RT, which has units of energy. In this case, energy per mole. So it'll cancel this all out here. Right? Integrating VDP, that has units of energy. RT has units of energy. This is unitless. Right? Everything inside a logarithm has to be unitless. Everything inside an exponential has to be unitless. So this all works out that this is a unitless expression and this is a unitless expression. dP is not very useful. Most of our equations of state are not pressure explicit. They're pressure explicit, not volume explicit. So we need to integrate with respect to volume for most all of our equations of state. So we can transform this expression into something that is more useful, albeit it looks much less pleasant. So instead of going from pressure equals 0, we're going to go from infinite volume. Same concept applies, ideal gas state. Now, we're not going through the derivation of this problem. I believe it is saved for a homework. Oops, sorry, PV over RT. Z, if you recall, is the compressibility factor. Ability factor. Most oftentimes when we've encountered the compressibility factor, it's when we use generalized compressibility factor charts. Is that ringing a bell for anyone from their process engineering or undergraduate thermodynamics class? Where you don't want to solve an equation of state, so you're lazy, so you just look at the generalized charts. Right? We typically think of this for vapors, like that have a small deviation, but you can calculate the compressibility factor for fluid as well. Right? We would just write Z of L, and you'd have, in this case here, the specific volume of the vapor. But you can calculate a compressibility factor for any fluid you'd like to. It's just strictly a mathematical substitution. So, same exact concept holds true, except we've transformed ourselves out of varying units of pressure to varying units of specific volume. The easiest way to do that is to use this expression here. So, I'll give you a little hint, because this will come up a couple times in your homework. When we're transforming from pressure to volume, it's the same thing that we did last class when we shifted this down a little bit, because we want to integrate, typically we want to integrate this area here with respect to the x-axis. That's what we're more comfortable with. We had to do it in class with respect to the y-axis. So I showed you an equation where you did actually accomplish that task by integrating it down that way. But typically what you have to do, if you take the partial derivative or you differentiate changes in pressure and volume, this is equal to P dV plus V dP. And you can also do the same thing with the compressibility factor. Let me write it out a little bit differently. So when you transform yourself out of varying pressure into varying volume, if you solve for this dP term, right, which we need to substitute into here, we end up having this lingering dPV term, which we can convert into this more useful unit called Z. So this pathway here, and then manipulating these calculus expressions is how you transform from here into there. And these terms kind of pop up. But this is the trick that we like to use in order to accomplish the task. Right, but the idea here, I mean, we've got some other lingering weird terms, right? But this is just strictly a mathematical substitution, right? We could take these and retransform them into PVs, RTs, right? So don't get confused by these expressions. This is just a substitution to make it more compact. The concept of fugacity is still baked in here perfectly, except the roles have switched a little bit. This is our ideal gas expression. This is our real pressure that we would substitute in an equation of state. So we could potentially substitute in here our real fluid equation of state. Right? When we choose an equation of state, we're implicitly saying that we trust and fully believe that that fluid follows that fluid phase behavior. Right? So whatever fluid you're looking at, all would behave this way. So every van der Waals fluid behaves identically, every Pang-Robinson fluid behaves identically. The only difference is relative to the critical point. But if I were to plot the reduced pressure and the reduced specific volume, where the reduced pressure is the pressure over the critical point, the reduced specific volume is the specific volume over the specific volume at the critical point, every single fluid behaves exactly the same, according to whatever equation of state that you've selected. Questions so far? We're just kind of grinding through some definitions. All right, this is one half of the puzzle. Our goal is to use the fugacity to help us solve phase equilibrium problems. And we have an expression that allows us to calculate explicitly, I mean, you do have to integrate it, but it is an explicit expression where I substitute in my equation of state. I have to integrate this expression. The only complication is that the specific volume, right, that I'm integrating, this point right here, corresponds to the specific volume of the vapor. This point right here corresponds to the specific volume of the liquid. The only complication is that the limit of my integration, right here, is the solution to the equation of state. Now for the ideal gas law, it's very trivial, right? You can rearrange it. But for a standard cubic equation of state that are pressure explicit, we have to solve a cubic polynomial in order to know how far I have to integrate this expression to. But what most code does is for specified equations of state, they just generate explicit equations. Or they've got really, really well baked in code that knows how to integrate and solve this really quickly. So the solution to a lot of thermodynamic problems are very, very algorithmic. You solve it once, you set up the algorithm, and then you can just substitute in whatever data you want, whatever equation of state you want. And so that's when you see thermodynamic data presented in a paper or discussed, it's very terse, it's very quick. Because the assumption is, this is all math has been worked out. Right? So that's why oftentimes when you're not familiar with thermo data, and you go through and you read a paper that's focused very heavily on thermo, it just seems like they're making it up. And they just generate these massively elaborate plots and say, oh yeah, duh, we just solved the phase equilibrium using the Pang-Robinson equation. Right? The assumption there is that we understand the algorithmic nature of thermodynamics and the system of how you can extract this kind of information from an equation of state. But from an outside perspective, when you start reading these papers, it seems like they're just making it up. Okay, one half of the equation. We now have an expression to calculate the fugacity of a vapor. We need to set that equal to the fugacity of the second phase. For our purposes, we're going to be most interested in liquids. So we need an expression for the fugacity of a liquid. The problem is we have a discontinuity here. So what we're going to do is we're going to break it up into two different steps. We're going to integrate it, step one, from an ideal gas state to the saturated vapor. Step two, saturated vapor to saturated liquid. Step three, we're going to pressurize the liquid even further. And we're going to develop an expression for that. So 3 steps. We're going to go from the ideal gas state to saturated vapor. We're going to go from a saturated vapor to a saturated liquid. And then finally, we're going to go to a saturated liquid to a subcooled liquid. Okay. So I'm going to take this general expression here. It's even to be slightly more rearranged just to make this as confusing as possible. Oops. All I did was move the RT over to the other side of the equation. So this is our first step. We're going from an ideal gas state, pressure equals 0, to the saturated vapor, which has a pressure of the vapor pressure for whatever the system temperature that we are investigated at. Right, that's our first step, self-contained. That's the fugacity of saturated vapor. Now we have to go across a phase transition here. So this is kind of just a little bit hand-wavy math, because basically, what is the fugacity change going across to phase transition? 0. The pressure is constant, the fugacity is constant, so this delta goes away. So this whole term goes to 0. And that's why I have kind of a hand-wavy notation there. The delta F over P of a phase change, but it doesn't matter because it goes to 0. The final step is we're going to go from a saturated liquid to a subcooled liquid. So here are our 3 steps. Step 1, step 2, which doesn't matter, and step 3. So we can rewrite this. This first term right here is just the fugacity of a saturated vapor. Right? So that means the liquid fugacity is just the saturated vapor fugacity times by this additional term right here. Okay. So what we're going to do is we're going to play around with that last little term, see if we can simplify it down a little bit, and we'll call it wraps on the fugacity of a liquid. Okay, so let's partially integrate 3. This expression 3, so this term right here, we're going to partially integrate it and manipulate it a little bit. So with integrals, we can always break it apart, adding and subtracting different aspects of it. So I'll say 3 is equal to, we'll break it apart. All right, so integrating 1 over x is just the natural log of x, subbing into limits of integration. we get the pressure over the vapor pressure. Now, if we substitute everything together, we go through a little bit of the manipulations, we realize that pressures cancel out. What we ultimately end up with is that the fugacity of the liquid at some temperature and pressure conditions is that it is equal to the fugacity of the saturation point at that same temperature, because we could potentially continue to pressurize it beyond the saturation point. That's what this last expression is here, right? We're going from the saturation point to some arbitrary system pressure. But then we have an additional term here. This is our fugacity of a liquid. So the fugacity of a liquid is equal to the fugacity of the saturated fluid. This is the same thing as the fugacity of the saturated vapor as well. And then we have this additional term right here, which is what we call the Poynting correction. Generally, this only matters for relatively high pressures. Let's say 1,000 psi or higher. But it's very easy to calculate to see when it should become impactful. So there's a couple of approximations that we can do to that Poynting correction. This is an exact expression. We have made 0 assumptions. So this is valid across all phase transitions, whether it's solid liquid, vapor liquid, whatever the case is. This expression is fully valid. It's for a single component, so I guess it could be gas solid. This is a valid expression as well. Now, what we can do is we can simplify this if the volume of the fluid is approximately constant, right, meaning that the volume of the fluid doesn't change very much with respect to changes in pressure, which is going to be a very reasonable expression. We can pull the volume out of the equation and integrate the expression. This is going to be a pretty good approximation unless you're going to extreme pressures. We're talking megapascals, gigapascals, where you're really going to start to see the fluid respond to changes in pressure. And the last one, if your fluid is an ideal gas, its saturation fugacity is simply equal to the vapor pressure. Okay. Let's take a moment and actually talk about this Poynting correction here. For the most part, we're not going to ever have to worry about it. The reasoning behind this is that for most of our phase equilibria, we're going to be focusing on relatively straightforward systems, meaning where the system pressure is near to the vapor pressure. And in fact, most all of our systems that we're going to be worrying about, that is going to be the case. because most of the emphasis in the class is going to be on phase equilibrium and understanding why phase equilibrium behaves a certain way. But when we do multi-component systems, things start to behave a little bit weirdly. So I want to introduce a multi-component system a little bit ahead of time, but it's in a way that most everyone has seen before. The TXY diagram. By show of hands, who is familiar with the TXY diagram? Who's heard of it at least? Okay. So the TXY diagram is intended to be a compact way to demonstrate phase equilibrium results. So basically the TXY diagram, where the temperature is equal to pressure is equal to a constant, we are varying the temperature of the system and the fluid composition. I like to use the notation Z for total composition because the typical nomenclature system that we use is Y corresponds to the vapor mole fraction, X corresponds to the liquid mole fraction, Z is the total composition. Now in fact, let me put Z of A, the fluid A. So for a binary mixture, we draw TXY diagrams based on the most volatile component being on the x-axis. So if we take a pure fluid right here, this is going to be Z of A equals 0, or the mole fraction of B is equal to 1. This is the mole fraction of A is equal to 1, and the mole fraction of B equals to 0. At low temperatures, regardless of the composition of the system, what phase are we in? Liquid. At high temperatures, what phase are we in? Vapor. I kid you not, every time I draw these diagrams, I do this for myself. It's my own consistency check. Because when you switch to PXY diagrams, it's opposite. At high pressure, you're liquid, and at low pressure, you're vapor. Okay, so at some point on this curve, on this axis right here, I am at pure fluid B. And at some point, there is going to be a phase transition from a liquid to a vapor as I increase the temperature, right? Same thing holds true on the other side. At some point, there is going to be a phase transition from liquid to vapor. If fluid A is more volatile, does that mean it boils at a lower temperature or a higher temperature relative to fluid B? Lower. So when I draw out my saturation temperature for fluid A, I should draw it down here. This will be my saturation temperature for pure fluid A, meaning it's got more of this space up here where it's a pure vapor. Then for fluid B, it's going to be up here, and this is a TXY diagram. Now using Raoult's law, this is something that I think most everyone should have seen before, especially if you're coming from a chemical engineering background. From a chemistry background or different fields, I am not 100% on the approach taken to fluid phase equilibrium. We get a window that looks a bit like this, depending on the relative volatility of the two different fluids. Now we can get a lot of different complex shapes, right? Azeotrope looks like something like this, right? Where you've got a minimum or a maximum. So you can get all sorts of funky different shapes growing out of TXY diagrams, because real fluids behave very, very complexly. Okay, so let's ignore the dashed lines for the weird non-ideal fluids that are not going to be the topic of discussion. Let's talk about these two curves. What's this one here? What's it called?
That's a bubble curve?
That is the bubble curve. That is the transition from a liquid to the two-phase region. So then this line up here is the, which curve? Do curve, transition from a vapor to the two-phase region. Now for most fluids that we worry about, for pure fluids, the bubble and the do curve are at exactly the same point, which is the saturation temperature. So if I'm condensing, a pure system of water into liquid water, it's only going to happen at the saturation point. If I'm boiling a pot of water, it's only going to happen at the saturation point. For a multi-component system, that's not the case, right? So in a multi-component system, if I choose some arbitrary point right here, obviously it's a really big one, okay, I'm going to have liquid and vapor. Now the complexity, when we're going to have to run into a situation where the Poynting correction matters, right? I'm going to highlight why it matters for all of them, and then we just kind of subsequently ignore it. So, I'm at a point right here in the middle of my TXY diagram. I have both liquid component A, vapor component A, and I have liquid component B and vapor component B. If we recall how to read our phase diagram, we know that we can get the liquid composition from a bubble curve, and we can get the vapor composition from the dew curve. Again, the convention, X corresponding to liquid properties, Y corresponding to vapor properties. So what I've done is I've set the system temperature, I've set the system pressure, and I've set the system composition. From that information, I can read off all of the necessary properties I'd like to about the system. So this corresponds to the mole fraction of A in the liquid. This corresponds to the mole fraction of A in the vapor. And we'll notice that we have both liquid and vapor of both fluids. But this doesn't make any sense. Because according to the pure fluid properties, A at the system temperature wants to be 100% vapor. Right? B at the system temperature, it wants to be 100% liquid. Meaning that in order for us to actually apply our fugacity relationships, we have to essentially calculate the properties of a fluid that doesn't really exist. And that's where things start to fall apart a little bit. So why do we care about knowing the fugacity of a fluid far away from its saturation point? This is the saturation of the pure fluid, meaning the fugacity following along this line here or this line here. So the issue with multi-component, multi-phase systems is that they are tricky. Meaning we have hypothetical fluids on either end. Because when I'm doing my multi-component, multi-phase thermodynamics, I'm going to choose a very specific, well-defined path. Just like when we're doing state changes, I would follow an isothermic line, then an isobaric line, then an isothermal line, whatever the case is. I'm not going to vary two things at the same time. Now when it comes to mixing fluids, I am certainly not going to waste my time trying to calculate the property changes across the temperature pressure path of a mixed fluid. No way. Way too tedious, way too complex. So instead, I'm going to calculate the properties of a pure fluid at some temperature and pressure, the properties of a pure fluid at some other temperature and pressure, and then I'm going to blend them isobarically and isothermally. Meaning that I'm going to fix my point right here for fluid, this will be fluid B, and then fix my point right here for fluid A, and then I'm going to blend them into this point right here. Which means that I'm going to have to calculate the properties of a fluid that doesn't necessarily exist, right? Because I'm going to need to calculate the properties of vapor fluid B, even though it wants to be a liquid. I'm going to have to calculate the properties of liquid fluid A, even though it's going to be a vapor. And this is why it's important for us to keep track of all the different changes and properties that happen when we're looking at the fugacity at some sort of analytic pressure. So if we're doing this phase equilibria for really, really high pressure fluid, like so it'll be a fluid that would naturally be very solidly in the liquid state. But then when you introduce a new material, you can have interesting and complex phenomena that happen for multi-component systems. That's where the Poynting correction is going to be really important. Or if I'm looking at a crystallization process of a high pressure fluid, I'm looking at the phase transition from a liquid to a solid, I'm also going to need to know the fugacity at that arbitrarily high pressure as well. So that's the motivation for why we're going through all this tedium at the moment. Now there is no easy way to do this kind of calculation, right? So all of the elegance and beauty of thermodynamics kind of falls apart when we start to deal with multi-component, multi-phase systems. It's because it's not a fault of thermodynamics, it's just a complexity of the real world. So we have some good systems and some good rules, and at the end of the week, we're basically going to be transitioning to multi-component systems, but you have to remember that this is the best we've got. So we're learning the system of thermodynamics that's been used to solve a lot of complex problems. So the fugacity, to wrap things up and point you in the right direction for the homework, right, you're going to be using these expressions that we derived for the fugacity to help you solve phase equilibrium of a van der Waals fluid. So you can use the integration approach looking at VDP, but I'd really recommend sticking to fugacity moving forward. Okay. All right, so I will be posting that homework today. Might be very late, we'll see how it goes. But anyway, have a good week.